Hello, we are Team 4, and this is our final analysis and redesign of a can opener. Can openers are used to open cans made of steel and aluminum. A can opener gives a safer, convenient, and more efficient method to opening a can. Based on statistics, we found that approximately 390,000 can openers are sold a year, and based on this, we decided to produce 100,000 units annually. Our primary consumer would be people and businesses that need to open cans. Our secondary consumer would be people and businesses that need to open both cans and bottles. This is our bill of materials and the exploded view of the can opener that we will be redesigning.
So here's our fast chart for the can opener. So the main function of the can opener is to open the can, and that is realized by the primary function of removing the lid. And you can see as the chart continues, you can see what functions contribute to removing the lid. Here's our functional component mapping matrix, where you can see which components realize what functions. As seen in the chart, some functions are realized by multiple components, which gives us room for redesign. Here's our DfMA chart, and the main part we want to focus on is this bottom right corner, where it's both high functional importance and also high assembly costs.
In this product family design, we see the function of the can opener, such as cut metal, maintain contact, etc., are all similar to customer groups with the one exception of open bottles function. As seen in the slide, the lower frame is the module and the remaining components are the platforms. This is an exploded CAD view of the can opener redesign. The design of the exploded view on the left only fulfills the primary customer's needs, which is the can opener function, while the design on the right fulfills both primary and secondary customers' needs, the can opener and bottle opener. This is the family assembly sequence. In the original sequence, it shows the two separate assembly sequence that serves both customer groups separately, can openers and bottle openers, ending with two final assemblies. In the second sequence, it shows a modified assembly that serves both customer groups with a single final assembly.
When we did our process selection for the upper frame, we decided to go with a level 2 tolerance and a decent surface roughness, given the intricacies of the part. When we did our process selection for the lower frame, we also decided to go with a level 2 tolerance and a decent surface finish, given the holes and outline of the part.
First looking at the upper frame DfM, from our calculations, we found the material cost to be about 76 cents, the casting to be 12 cents, and the die cast cost to be 46 cents, which led to a total of $1.34 for our original part. After the redesign and reducing material, removing sharp edges, and removing inner depressions as our design guidelines, we found that the material cost greatly decreased to 43 cents, and then with a casting cost of 15 and a die cost of 36 cents, the total price was 94 cents, which was about a 29.8% reduction. For the lower frame DfM, we found the material cost to be $1.02, the metalworking cost to be about 2 cents, and the die cost to as 0.0256, with a total of $1.06. And the DfM Pro offered 0 recommendation for the original part. After the redesign and reducing material, minimizing steps, and removing sharp corners as our design guidelines, the material cost also greatly decreased to a value of 62 cents, and the metalworking cost was about 1 cent, and the die cost was about 0.0163, with the total being $0.646. With a 39.1% reduction. The DfM Pro offered a few recommendations, such as the cutout distance to part edge. And we checked hubs, and after using extrapolation with Excel, we found that the before cost was around 65 cents, and the original was 0.264, with a percent reduction of 59.5%.
So here's our estimation for the manual assembly time of the original design. So some assumptions that were made during this estimation were that the parts placed on the upper and lower frame pins, such as the cutting blade and the gears, were close fit and therefore would have some resistance to insertion. Another assumption was that the pin clip and the gear wheel or the final fastening steps on their respective pins, which contributes to the insertion time. And the third assumption made was that the blade would need to be handled with grasping tools because it's a sharp object. And after going through the estimation, we found that the manual assembly time of the original design would be about 70 seconds.
This is the manual assembly of the redesign. There were changes made based on the DfM/A chart on slide 7. There were redesigns made on the lower and upper frames and main pivot pin, as the manufacturing, assembly cost, and functional importance were both in the high category. Due to a new design of the subassembly, the previous lower frame pin was removed and replaced with a pin identical to the upper frame. Because of the lower and upper frame were redesigned, the insertion time per part were reduced for the gear wheel, lower frame pin, and main pivot pin. The total assembly time was reduced by approximately 7.76 seconds based on the redesign.
For the automatic assembly, we focused on the subassembly that would attach to the crank handle. This consisted of the lower frame, handle clip, gear wheel, gear, and the lower frame pin. This analysis assumed a close fit between the lower frame pin and the lower frame, gear wheel, and gear. Other assumptions include the lower frame pin being the final fastening step in assembly, and that the part feeders would operate at a desired speed of approximately 4 parts per minute. For the original design of the subassembly, the total assembly cost was approximately 14.99 cents. For the redesign, in accordance with the DfM chart on slide 7, the lower frame and lower frame pin were both modified as shown in the images below the table. With these modifications, the total assembly cost of the subassembly was 14.81 cents. This results in a cost reduction of 0.18 cents per can opener manufactured. While this may seem negligible, during mass production, small reductions like this can still be very beneficial as they add up over time. Additionally, the changes made to the lower frame pin and lower frame reduce costs elsewhere outside of this subassembly, thus this result does not fully represent the entire cost reduction.
So here's a look into our product service system for the can opener. The premise is sort of like a lifetime warranty where the customers can return their used or broken or old can openers in exchange for credit, and they can return these either by shipping them to our facility, or we can have drop boxes located in local areas. And based on how the can opener is returned, they will be given some amount of credit, but every can opener return will result in some credit, because by returning the can opener, we can use these can openers and disassemble them and salvage some parts for reuse in new can openers. And we can also guarantee that parts that can't be salvaged are recycled and disposed of properly. So it's also beneficial for the environment.
The upper picture is the original and the lower is the redesign. One critique of our redesign is that the main pivot pin was resized as a result of the upper frame width change. Another is that the pin blade clip was added to the lower frame subassembly and increased the part count. Our last critique is that the upper frame's handling could be affected as the size was reduced. Through all of this, we still improved our costs for assembly and manufacturing while keeping the aesthetic look and functionality of the can opener. Thank you.